this video, we will go to take up one more problem on the overhanging beam. The problem number 36. Draw the bending moment and shear force diagram for the beam loaded as shown in the figure. We have a beam which is of 8.5 plus 9.5, which is 18 meters span, having simply supported at the point A and point B and overhangs by 3 meters from A towards C and 4 meters from B towards right towards E by 4 meters. So we have an UDL, uniformly distributed load, for 30 kilonewton per meter for a span of 8.5 meters from C to D, and also there is 1 point load of 100 kilonewton acting downwards at the point E. From the distance between the point D to the support B will be equal to 5.5 meters. Now to find out the support reactions, so first we will going to have taking the moments about the point A. Once you are taking the moments about the point A, which will be equal to RBV into 10.5, because you have 5.5 here, and from here it is 8.5 minus 3, which will going to be 5.5. So 5.5 plus 5.5 becomes 11. So RBV into 11 will be equal to 100 into 100 into, so here 9.5 plus 5.5, which is 15, plus 30 into 8.5 into 8.5 by 2 minus 3. So that will be equal to RBV, which is 165.34. So then we have RAV plus RBV will be equal to 8.5 into 30, then plus 100, which will going to give you RAV will be equal to 355 minus 165.34, which will be equal to 189.66 kilonewton. So once you get that, then we will have the shear force diagram. SFD will be equal to, SF at C will be equal to 0. SF at A will be equal to minus 30 into 3, minus 30 into 3 plus 198.66 kilonewton, which will be equal to plus 99.66 kilonewton. Then SF at D will be equal to plus 99.66 minus 30 into 5.5 will be equal to minus 65.34. SF at B will be equal to minus 65.34 plus 165.34, which will be equal to 100 kilonewton. SF at B will also be equal to plus 100 kilonewton. Now we will going to get the shear force diagram. SF at C is 0. Then SF, when you are considering at the point A, we have two loads which is acting. One is on the UDL and the another one is the support reaction at the point A. SF at A will be equal to, it suddenly drops from 0 to minus 90 kilonewton because due to UDL by the equation of straight line, and it then changes suddenly from minus 90 kilonewton to plus 99 kilonewton due to the support reaction at the point A. And then SF at D will be equal to, and it drops from plus 99 kilonewton to minus 65.34 kilonewton according to the equation of straight line because due to UDL, and remains constant as there is no other load acting between D and B. It remains same at 65.34 kilonewton. At the point B, because due to the point load which is 165.34, it suddenly rises from minus 65.34 kilonewton to 100 kilonewton because of the point load at B, and that is the support reaction at the point B. And between B and E, SF remains constant at 100 kilonewton. Now we go for the next one, the bending moment diagram. So in the bending moment diagram, the bending moment at the point C, which will be equal to 0, bending moment at the point A will be equal to minus 30 into 3 into 3 by 2, which will be equal to minus 135 kilonewton meter. BM at the point D will be equal to minus 8.5 into, minus 30 into 8.5 into 8.5 by 2 plus 189.66 into 8.5 minus 3, that is 5.5, will be equal to minus 40.62 kilonewton meter. BM at the point B will be equal to minus 30 into 8.5 into 8.5 by 2, 8.5 by 2 plus 5.5, 8.5 by 2 plus 5.5 plus 189.66 into 11 will be equal to minus 400 kilonewton meter. BM at the point E will be equal to, again, minus 30 into 8.5 into 8.5 by 2 plus 9.5, and then plus 189.66 into here, this is 5.5, 5.511 plus 4, which is 15, plus 165.34 into 4, which will be equal to 0. Now when you are plotting this, we can see here bending moment at the point C, bending moment at the point C is 0, at A minus 135 kilonewton meter. Therefore, the line joining between 0 to minus 135 kilonewton meter is drawn by means of a parabolic curve because it is a uniformly distributed load. BM at the point D will be equal to minus 40.62 kilonewton meter. So you can't join between 40.62 to 135 kilonewton meter because between A and D, SF changes its sign from positive to negative. Therefore, you will going to get the maximum bending moment at that particular point. We need to find out the distance with respect to at what distance the shear force changes its sign, and also the bending moment, what will going to be the maximum bending moment, which we need to calculate. Then BM at the point B will be equal to minus 400 kilonewton meter. Therefore, it will going to drops down from minus 40.62 to minus 400 kilonewton meter linearly. Again, between BM at the point E is 0. Again, it varies linearly from 400 kilonewton, minus 400 kilonewton meter to 0 by linearly. So this is how you will be able to get this. Now we need to find out what will going to be the maximum bending moment. The maximum bending moment will occur at a point where SF changes its sign. SF changes its sign at A and F and B. Then let the distance of point F be x meters from C. Let the distance of point F be x meters from C. So then what happens? SF at F will be equal to SF changing its sign from positive to negative at this point. So that will be equal to 0. That will be equal to, that is minus 30 into x plus 189.66, which will be equal to 0. Therefore, x will be 6.322 meters from C. So the value of x will be equal to 6.322 meters from C. Once you get this point, now we need to find out what will going to be the maximum bending moment. So BM at F will be equal to minus 30 into x by 2 minus 1 plus 189.66 into x minus 3. So you know the value of x is 6.322. So you substitute that minus 30 into 6.322 into 6.322 by 2 plus 189.66 into 6.322 minus 3. So therefore, on simplification, you will going to get it as plus 30.535 kilonewton meter. So at the point F, you will going to have the maximum bending moment as 30.535 kilonewton meter. Then join between minus 135 kilonewton meter to 50.535 kilonewton meter by parabolic curve because due to UDL, and from there again from 30.535 kilonewton meter it drops to minus 40.62 kilonewton meter. You join that point, those 2 points also by means of a parabolic curve. Once you do that, so then the bending moment is changing its sign from negative to positive at the point G and also at the point H from positive to negative. Therefore, that is what is though. Therefore, we have the maximum positive bending moment at the point F will be equal to plus 30.535 kilonewton meter, and maximum negative bending moment is at the point B, which will be minus 400 kilonewton meter. So now the point of transfer flexure will going to come into the picture, where the bending moment is changing its sign. It is the point where the bending moment changes its sign. The point of contraflexure are at point G and H. Therefore, let the distance of point G be y meters from C. So that will be bending moment at the point G will be equal to 0. That will be equal to minus 30 into y by 2 minus plus 189.66 into y minus 3. So on expansion, it is minus 15 into y square plus 189.66 into y minus 568.9 it will be equal to 0. Therefore, y square minus 12.644 into y plus 37.932 will be equal to 0. Therefore, by using the quadratic equation, y will be equal to 12.644 plus or minus root of 12.644 square minus 4 into 37.932 by 2, which will be equal to 7.745 meters or 4.895 meters. Therefore, the point of contraflexure at G is 4.895 meters from C, and the point of contraflexure is at H is 7.745 meters from C. So this is how you will be able to solve this particular problem. You can see here y will be equal to 4.895 meters from C for the point G, and for the point H, which will be Z, which will be equal to 7.745 meters from C. So this is how you will be able to solve this particular problem. Thank you.